Good morning for those of you in the U.S., and good afternoon for those of you joining us here in Europe. My name is Allison Douglas, and I'm the Market Development Manager at Agilent Technologies, and I will be your host today for the webcast entitled Signal Analyzer Fundamentals and New Applications. This webcast is second in a series aimed at educating our customers on fundamentals of RF and microwave measurements. We'll begin today's webcast in just a moment, but first let me explain to you a little bit about the system. WebEx Event Center allows you to sit back and have the presentation material advance automatically. To participate in the Q&A session, you can enter questions at any time during this presentation in the question window on the lower right-hand side. Our team of spectrum analysis experts, Bob Nelson, Keith Leach, and Scott Latham, have joined us today to answer questions at the end of the presentation, but again, please feel free to enter them in the Q&A window at any time. Be sure to address your questions directly to all panelists by clicking on the pull-down menu. We have a lot of people online with us today, so I apologize in advance if we don't get to all of your questions. But don't worry, if we do run out of time, we will respond to the remaining questions via email. We will also ask that you take a moment to fill out the short feedback form that will appear when you close the WebEx session. Now let's move on to the presentation. Joining us today is Eric Diaz. Eric is a Senior Product Manager in the Agilent Technologies Microwave and Communications Division in Santa Rosa, California. In his 32-year career with the company, he has held numerous roles in marketing, R&D, and application engineering related to a variety of signal analysis and generation products. Eric holds a BSEE from UC Davis and an MSEE from UC Berkeley. Welcome, Eric. You now have the floor.
All right. Thank you, Allison. Well, hello, everyone, and welcome to our webcast on Signal Analyzer Fundamentals and New Applications. As the name suggests, this session is targeted on signal analysis basics. Now, signal analyzers are very versatile instruments, and they can be used for a lot of different applications. So if we wanted to really cover things in depth, we'd be here for several weeks. But of course, we only have 1 hour, so we won't be able to do that. But for those of you who are new to signal analysis, I hope you find this interesting. And for more experienced listeners, I hope you learn at least a few useful nuggets of information. All right, so let's get started. Well, here's our agenda for the next hour. And as you can see, we'll start with a quick introduction and do a simple overview to review, what is spectrum and signal analysis and what are the kinds of measurements that people might make with these instruments. Then we'll spend a little time on the theory of operation, the architecture of how we actually put these instruments together and how they work. And then we'll take a look at some of the important specifications that people are interested in when they use these instruments, of, what kind of performance does it need to have. And then we'll spend a few minutes looking at some of the modern developments that have occurred in signal analysis and some of the new capabilities that are available. And then finally, we'll just wrap up, and we'll have a Q&A session at the end for any questions that come up. And so that's how we're going to proceed. So a good place to start out is to talk about a few definitions. Now, a spectrum analyzer, classically, that's an instrument that gives you an indication or a measure of the amplitude of a signal versus frequency. And so that's really a scalar type measurement, scalar information, and that's how spectrum analyzers first began some 50 years ago with this kind of capability. Now, sometime after that came the introduction of a vector signal analyzer, which provides not only magnitude information, but also phase information, typically over some finite IF bandwidth of the instrument. And so this new capability, by adding not only the magnitude, but the phase information, gave us the ability to do additional kinds of measurements, to do things like error vector magnitude and code domain power and so forth. So it added a lot of, really a new dimension of capability. Now, in the last decade or so, combination of these two capabilities for spectrum analysis and vector signal analysis have been combined into a single instrument, and that's what we call a signal analyzer. So it provides, rather than having two separate instruments, now it's all in one. And I think for historical reasons, because the term spectrum analyzers have been around for so many years, often spectrum analyzers and signal analyzers, those terms get used interchangeably. But in practice, I'd say most all modern instruments are really signal analyzers. So if you hear me use both terms in the presentation, that's where it comes from. All right, so looking at the time and frequency domains, let's say we start off looking in the time domain, which is the amplitude versus time plane here that we look at. That's really an indication of or what we see on an oscilloscope. So you see the vector sum of all the frequency components of the signal that make up the overall trace that we see on the oscilloscope. Looking at the same signals in the frequency domain, we can see the individual components that make up the overall waveform, as you see here. So it's really two different ways of looking at the same signal. Now, in terms of the kinds of displays that we might normally see on a spectrum analyzer, here's a few examples. So this one here is a pulsed RF signal, so you can see that sin X over X type characteristic of the classic characteristic of pulsed RF signal. Up here, this is some type of communication signal, maybe a WCDMA type signal, digital modulation. And then over here on the right, we have perhaps a fundamental signal and maybe a harmonic that's appearing. So these would be narrowband signals. So you got just a sampling of the kinds of signals we might see on a spectrum analyzer. Now, there are a couple of different approaches to displaying amplitude versus frequency. One approach would be to use an FFT analyzer. And conceptually, you can think of this as an instrument with a whole bunch of parallel filters. And so wherever signal energy exists, like here at F1 or at frequency 2, you would get a response here on the display because that signal energy would be passing through one or several of these filters. Another classic approach is what's called a swept analysis. And again, conceptually, you can think of this as a bandpass filter that sweeps across a frequency. So as we go from the start to the stop frequency, every time this filter encounters some signal energy, again, you would get a display on the screen. And this architecture of a swept analyzer is, again, the traditional spectrum analyzer architecture that's existed for 50 years. So with these basics in mind, as far as the applications of where it can be used, there's all kinds of different uses for it. People use spectrum analyzers for spectrum monitoring to maybe look at broadcast spectrum and make sure that people are operating within the assigned frequency that they were given, and maybe check to make sure that it's not spilling over into someone else's channel and causing interference. We might be using it to measure spurious emissions, where you get, in addition to desired signals from a transmitter, you might get some unwanted signals at unwanted frequencies. So those would be spurious. A spectrum analyzer can be used in conjunction with a signal generator to measure the characteristics of various components, scalar network analysis type mode. We might use it to do noise figure measurements or phase noise measurements or various kinds of distortion measurements. One of the big applications is to look at modulated signals. These could be analog or digital or pulsed RF type modulation. In recent years, we've seen a big increase in wideband signals and performed the vector analysis on that. And of course, another very popular application is EMI, electromagnetic interference or compatibility testing. And so these measurements can take place over a huge amplitude range, anywhere from practically down to KTB noise up to, say, plus 30 dBm. over a very wide frequency range, from very, very low frequencies up into sub-millimeter range. All right, so let's now take a look at the architecture of how one might actually build a spectrum analyzer. So here we've got a simplified block diagram. You can see over here on the left, the incoming signal would go into the RF input. And typically the first thing you'll run into would be an RF attenuator. This gives us some ability to control the signal level coming in. In particular, if you have high-level signals, you want to add enough attenuation to bring that signal level down to make sure that you're not overloading or causing distortion in the mixer, or worse yet, you could even damage the front end. Typically, the next thing you'll find in the signal path would be some kind of filtering. Often this is called a pre-selector filter, in particular on microwave spectrum analyzers. Some RF spectrum analyzers get by with simply a low-pass filter. And the idea here is to limit the bandwidth of the incoming signal, again, to limit the amount of energy that eventually reaches the mixer. Now, it's a basic super heterodyne architecture, so we have a local oscillator here that mixes with the incoming signal in the mixer to produce an IF signal. And once we're in the IF, we'll have some combination of gain and attenuation to give us level control within the IF. And then we hit a very important part of the instrument, which is the IF filter, or also called the resolution bandwidth filter. And again, this gives us the ability to resolve the signal as appropriate for the signal we're looking at. At that point, we then go through log amplification, since the typical display would have a log amplitude display. And then we go through some detection through the envelope detector and some video filtering, and eventually that drives the vertical component of the display. Now, the horizontal component is driven by the sweep generator, which also controls the LO, so that determines what our start and stop frequencies are. So this would be a typical display, and some of the areas I'll point out. Up at the top, we have what we call the reference level, and that's the reference point at which we start to measure the signal. And as you can see here on the left, we have a log scale. In this case, it's shown as 10 dB per division, although we could make that 1 dB or 5 dB or 20 dB per division as appropriate for our signal. On the x-axis, we have our start and stop frequencies, although, again, some people prefer to view the signal in terms of a center frequency and a frequency span. So generally, that's a user selection, depending on how you like to look at the spectrum. Again, depending on application. All right, so as I mentioned, we have the incoming RF signal, in this example, let's say at 1.5 gigahertz. And then our LO will be sweeping, and in this example, we're going from 3.6 to 6.5 gigahertz. And so as the LO sweeps, when it combines with the incoming signal, we will get several different new signals coming out. Of course, the mixer is a nonlinear device, and so we end up with new frequencies that didn't exist before, and that would be the sum and the difference frequencies. And in particular, the one we're most interested in is the difference frequency, between the difference between the LO and the incoming signal. That's going to be our IF frequency. Now, in the IF, when we apply filtering, the resolution bandwidth filter, depending on the filter bandwidth we select, that gives us the ability to resolve signals that might be close together to a greater or lesser degree. So here you can see as we have two signals close together, when I go to the narrow resolution bandwidth, I can see those two individual responses much better. After filtering, then we reach the envelope detector, and this would strip off the envelope, so the rapidly varying signal that you see here is the IF frequency, and then any modulation that might exist on the signal would then be here on the envelope. So that's the part we're interested in. And from there, then we go to the detector. Now, detection is an interesting topic because there's a lot of different ways that you could detect the signal. So let's say that here on our display, since it's always a digital display, really what we're doing is we're dividing the display into a bunch of fine-grained tiny frequency slices that we call frequency bins or buckets. And so the number of buckets across the screen, it can vary. It can be anywhere from just a very small number, 20 or 50 points, all the way up to 40,000 points. But nevertheless, each one of those buckets represents a tiny slice of frequency. And so for each one of those, if we were to pick the largest value that occurred in that tiny frequency slice, that would be what we call positive peak detection. And if you were likewise to pick the smallest value that occurred during that tiny slice of frequency, then that would be negative peak detection. Or I might take the approach and say, well, I'm not going to worry about the largest or the smallest value. If I just pick whatever value occurs at the middle of that bucket, that would be what we call sample detection, shown by the stars here. So again, depending on what you're trying to look at, you can select any of these different detector types. There's another important one called the average detector, and the way that works is within any one of these frequency bins, if we sample very quickly, so it's shown by all these X's here, and then took the root sum of the squares of all those values, then that would give you the average value that occurred in that particular frequency bin. So again, different ways of detecting the signal, and generally all these detector types are available in the spectrum analyzer. Now, after detection, then we have what we call the video filter, which is a low-pass filter. And the idea of the video filter is then to remove the higher frequency components of that signal to give us kind of a smooth effect. And this can be really useful, in particular when you're looking at very low-level signals. So here, for example, we have a signal that's just barely popping up out of the noise, and it's kind of hard to really see it very clearly here where you have a lot of noise present. So by using the video filter, you can remove the higher frequency variations, and then this gives us kind of a smooth response, and it's much easier to see the signal out of the noise. So applying video filtering certainly works to smooth out the noise. The problem with it is that as you reduce the filter bandwidth, it slows the sweep time down tremendously. And so if you're trying to cover a very wide span, then that can slow down your measurement considerably. So another approach that people use is to do what's called trace averaging or video averaging. So what that does is you take successive rapid sweeps, then you mathematically average each of the individual frequency buckets across the screen to come up with an average value. So here the yellow trace is the single sweep. The blue trace would be the average of 5 sweeps. The purple trace here is the average of 20 sweeps. And then finally, when we average 100 sweeps, we get this green line here. And so again, it's another approach to providing the smoothing function instead of using video filtering. If you added up the cumulative time of doing all these averages, it might not be too different than a single sweep of video filter, but the difference is you've taken multiple sweeps, and so you converge on this average value. So again, it's just another tool that's available, and depending on the kind of signal we're looking at, you might prefer to use video filtering or video averaging. Okay, now let's take a look at some of the important specifications that people are concerned with. These would include things like frequency range. I think that's probably the most basic one. You have to have an instrument that covers the frequency range of the signal you're interested in. Obviously, we're going to be concerned with the accuracy, both frequency and amplitude accuracy of the measurements we make. We'd like to have confidence that the value we read is actually accurate. resolution, sensitivity, distortion, dynamic range, these are all, again, very important parameters that as we make measurements, you want to make sure that you have adequate sensitivity and freedom from distortion and so forth. Now, this is probably a good point to mention that when we talk about specs, let's be clear on our terminology. So Agilent defines things this way. We say that specifications are a measure of a particular parameter, and it's a measure that we warrant. In other words, we say that we guarantee that it will meet this specification. Otherwise, if it's not performing to that level, then obviously it would be something that would be repaired under warranty or have to be repaired to meet that specification. And so specifications are usually stated over a certain temperature range. Typically it's 0 to 55 degrees C. Sometimes it might be a different frequency range, but that's typically what it entails. On a data sheet, you might also see typical values. And a typical value is something that gets measured on every unit on the production line. And statistically, it's a value that 80% of the units will meet to a 95% confidence level. And typically, this is over a more limited temperature range, somewhere in the room temperature type range. And we don't add measurement uncertainty to that value. But the idea is that a typical value gives you a reasonable idea of the performance that you can expect from the instrument. Then finally, we have nominal values. And these would be parameters that we don't necessarily test on every single unit on the production line. But again, it's to give you an idea of what to expect. And a good example of that might be that we design spectrum analyzers to have 50 ohm input impedance. So we don't necessarily test that on every single unit, but by design, it's designed to have that kind of impedance. All right, so as I mentioned, probably one of the most basic and important parameters is the frequency range. And so depending on your application, you might just need performance, say, to 3 gigahertz for RF applications, or you might need to go to 26.5 gigahertz or even 50 gigahertz or higher. So again, there are different models available of spectrum analyzers to cover these various frequency ranges. And typically what you'll find is that the very high frequency models that go up to 26 or 50 gigahertz may subdivide the overall frequency range into sub-bands, as you can see here. Now, if we read signal frequency on the display, you might obviously want to know what kind of accuracy can you get. And so let's say we put a marker on a signal and get some value. The uncertainty associated with that depends on several things. So, for example, how good is our frequency reference? So the better the quality of the reference, then obviously the smaller the uncertainty in our measurement. The overall accuracy is also going to depend on how wide a frequency span we've got. So if we are in a very wide span, we'll probably get less accuracy than you would in a very narrow frequency span. It's also a function of the resolution bandwidth that we select. Generally, with smaller resolution bandwidths, we get better accuracy. And then it's also going to be a function of how many display points we've selected. So if I choose 40,000 display points, I would have a lot better frequency resolution than if I had only picked 100 points across the screen. So all these things factor into the overall frequency accuracy. Here's an example of putting numbers to that. So in this case, let's say we're looking at a 1 gigahertz signal in a 400 kilohertz span, and if I'm using a 3 kilohertz resolution bandwidth and 1,000 points across the screen, if I plug those values into our calculation, you see that we end up with an overall uncertainty of 907 hertz. All right, now amplitude accuracy depends, again, on a number of different factors. So one of the most basic ones would be the input mismatch, or the voltage standing wave ratio. If I have a very poor match, there will be uncertainty associated with that. And for those of you who are familiar with network analysis, you know that that introduces, again, a big uncertainty into the amplitude. Now, one of the ways you can improve that, of course, is by adding attenuation at the input. That'll improve the match. But, of course, as you change that attenuator value, then that in itself introduces some uncertainty. Because we have broadband components that operate over a wide frequency range, there will be some frequency response associated with those components. And, you know, other things like we have IF gain and resolution bandwidth filters. Each of those will introduce a small amount of uncertainty. Again, anytime you have any active circuits like the log amp, again, that can introduce uncertainty. And then the calibration signal that we use has its own uncertainty. So you have to add up all these different factors to get the overall measurement uncertainty. All right, so the reference level is determined by our IF gain, and so there would be some uncertainty associated with that. I will say that with modern analyzers where a lot of this is implemented digitally, the magnitude of the uncertainty here drops off considerably, and so this really is much less of a concern today than it was 10 or 20 years ago. Likewise, display fidelity, again with modern analyzers where we use very high accuracy digitizers, the scale accuracy here is much, much better than it was in the past. Now, resolution bandwidths, you know, I mentioned it lets us resolve signals that might be close together. Here's an example of that. Let's say we have two signals that are 10 kilohertz apart. And if I use a very wide filter like this black trace shows, this might be 30 or 100 kilohertz bandwidth filters, the filter is so wide that we just basically capture the energy from both of those signals together, and it's very difficult to tell that indeed there's actually two signals present. If I use a narrower filter, let's say a 10 kilohertz bandwidth filter, then we get a more distinct response. And so in this case, you would see actually a 3 dB dip in between those two signals because of the 10 kilohertz bandwidth is selected. So if I have two signals of equal amplitude, if I select filter bandwidth equal to the spacing, that allows me to distinguish between those two signals. Of course, it's not just the 3 dB bandwidth. We have to look at the overall shape of the filter altogether. And so a good way to measure that is to do what we call the selectivity of a filter, which is the ratio of the 60 dB bandwidth to the 3 dB bandwidth. All right, and this becomes important when we're looking at signals that are different amplitudes. So here again, using our same two tones that are 10 kilohertz apart, if they create intermodulation distortion, those distortion products would be quite a bit farther down. In this example, they're about 50 dB down from the fundamental two tones. So with our 10 kilohertz bandwidth, it's enough to resolve the main tones, but notice that the filter skirts, because of the selectivity of this particular filter, we would not see the distortion product. And so if you want to see the distortion products, you have to use a narrower filter. In this case, these particular filters have a 15:1 selectivity ratio, so you would need a 1 kilohertz filter to see those distortion products. Now the good news is that, again, with pretty much all modern spectrum analyzers, we've gone from analog to digital type filters, which have much, much better selectivity than the old filters. And so in the past, a typical analog filter might have a 15:1 ratio. Digital filters are more on the order of 4 or 5:1. So they drop off much, much faster, which is a good thing, because then that allows you to see those small signals that might be close to the large signal. You can resolve them much more easily. So, you know, a narrow filter with good selectivity is important, but one other consideration we have to think of is the phase noise performance of the instrument. So if you have too much phase noise, again, when you have these small signals close to a large one, the phase noise may mask over and hide that signal completely. So generally the main source of phase noise would be the quality of the local oscillator inside the instrument. So the better the LO you have, the lower the phase noise would be, and hopefully avoid this kind of situation. So at this point you might be thinking, well, gosh, if narrow filters give us better resolution, why not always use a really narrow filter? And that would give you good resolution. The problem, or the price you pay for that, is that the sweep time slows down dramatically. In fact, for every 10 times change in bandwidth, your sweep time goes up by a factor of 100. And so if you try to sweep a narrow filter too quickly, you get this kind of a phenomenon where you lose amplitude and you get frequency pulling because you're just trying to sweep through that filter too fast and it just doesn't even have time to fully charge. So that's why you want to use a narrow enough filter to resolve the signals, but not too narrow to slow down your measurement too much. So here's some examples of the kind of measurement speeds you might get, say on one of our older analog instruments, the 8563E, for a 1 2 gigahertz sweep with 3 kilohertz filter, it would take 280 seconds. Now with a modern analyzer that has digitally implemented IF filters like the PXA, under those same settings, 1 to 2 gigahertz with a 3 kilohertz bandwidth, we've cut that sweep time down in half. But 134 seconds is still a long time. So an even better technique here would be to do an FFT, and you can see that we reduce the sweep time by an order of magnitude. We're down to 10.7 seconds, so much faster measurement using the FFT technique. Now, very often in spectrum analysis, we're trying to look at very low-level signals. And so the sensitivity of the instrument, or also called the displayed average noise level, becomes really important. So let's face it, we have a number of active circuits inside the instrument, and so there will be some amount of noise generated internally, and ultimately that's what limits our displayed average noise level. So the way we talk about sensitivity, we say, what's the smallest signal that you can measure above the noise? And remember that really what we're displaying is signal plus noise to noise. Now you might expect that when the signal equals the noise power, you would expect to see a 3 dB rise on the display. The reason we see something different here, it's 2.2 dB instead, is that remember we're going through a log amplifier, and so that changes the statistics of the noise from being a Gaussian distribution to a Rayleigh distribution. And so if you do all the mathematics of that, you find out that when the signal equals the noise power through that Rayleigh distribution, you get a 2.2 dB rise above the noise. Now, remember, going back to our architecture, well, the first thing we encounter after going through the RF input is an attenuator. And so the amount of attenuation, since that would directly impact the signal-to-noise ratio, the more attenuation you have, the worse your signal-to-noise ratio gets. And so here, for example, when we have 20 dB of attenuation on the right side here, you can see it's very difficult to even distinguish that there might be a signal there. By reducing the attenuation 10 dB, we improve that signal-to-noise ratio by that amount, and now it becomes a lot more apparent that there is indeed a low-level signal there. All right, another big important factor in the overall noise performance is which IF filter we select. And so the narrower the resolution bandwidth, the less noise is allowed to pass through the IF and reach the detector. And so here, for example, as we reduce the resolution bandwidth from 100 kilohertz to 10 kilohertz or 1 kilohertz, every time I get a 10 dB improvement in signal-to-noise ratio. So it's much, much easier to see that signal. Remember earlier we talked about using video filtering to smooth out the noise, and again, this doesn't really improve your signal-to-noise ratio, but it makes it easier to see those low-level signals. So again, that's a good tool to use for looking at those small signals. So if we were to plot out the performance here on a graph, where on the vertical scale we've got the signal-to-noise ratio, and then on the x-axis we have the power that's actually reaching the mixer, which is simply the signal power at the input minus whatever attenuator value you've picked. You would end up with a series of lines like this for each resolution bandwidth. So here, for example, would be the noise as a function of power at the mixer for a 1 kilohertz filter, and then if I reduce the bandwidth by a factor of 10 to 100 hertz, I'd get a similar line, 10 dB, shifted down by 10 dB. All right, so the rules then for achieving the best sensitivity, you want to use the narrowest resolution bandwidth possible with the least amount of RF attenuation. You want to apply some type of averaging, could be video or trace averaging. If you have a preamp available, that again is another way to improve the overall sensitivity. And then some instruments like the PXA have a few extra tools, things like the low noise path or noise floor extensions. And I won't discuss those here because that's kind of beyond the scope of the basics, but again, those are some techniques to give us better overall sensitivity. Now let's look at the other side of the coin. Let's say I have a very large signal. Well, then I have to worry about distortion. And so let's say here at the input I've got some kind of signal, and it might have, here we show some harmonic distortion. Now as you go through the signal chain in the analyzer, obviously those signals would be translated down to an IF and eventually detected. But what happens if I'm also generating distortion products inside the mixer, inside the instrument? So they're not part of the original signal, but they're created inside the instrument. Then you would end up with an overall measurement that is a combination of the actual signals at the input and the distortion products. So obviously that's a situation we'd like to avoid. So distortion, as you know, there are different kinds of distortion. We have things like intermodulation distortion or harmonic distortion. And generally we classify these as by the order of the distortion. So second harmonic would be second order distortion, a third harmonic or an intermod would be third order product, and so forth. And they behave in slightly different ways. So generally what you find is that, let's take a look at second order distortion. For every dB increase that we have on the fundamental signal, the second harmonic would increase by 2 dB, so it rises twice as fast as the fundamental signal. And then third order distortion rises 3 times as fast, so I would get a 3 dB increase. And intermodulation distortion is often considered third order distortion, and you can actually have fifth order and seventh order and so forth, but the most important one here typically is third order product. So since they rise faster than the fundamental, we could actually plot, again, our distortion as a function of power reaching the mixer. And as you can see, the distortion, the second order distortion would rise up with a slope of 1, whereas the third order distortion, since it's rising even faster than the second order, would have a higher slope here. Now, if you sort of projected out to the point where the signal to distortion ratio finally reaches 0, in other words, the distortion product would be as big as the fundamental, those points are known as the TOI, or third order intercept, or SHI, the second harmonic intercept. In practice, you'd really never reach these points because the distortion would be so terrible, you just couldn't make any measurements. But nevertheless, TOI and SHI are good measures of the distortion performance of the instrument. So if you're concerned that you might have some combination of distortion along with the signal you're trying to measure, a classic test for that is to do the attenuator test. And so this is where we add some attenuation. And so if let's say I add 10 dB, if the signal stays at the same point on the screen and I just increase the noise by 10 dB, then that's a sign that we're measuring a real signal. If, on the other hand, if I add 10 dB and the signal level drops, then that's a sign that I was looking at internally generated distortion. So it's a very simple test, but very effective. All right, so on the one hand, we're concerned with distortion. At the other end, we're worried about ultimate limits on sensitivity or displayed average noise level. So what we really want to do is maximize our dynamic range, which is the ability to look at both large and small signals on screen at the same time and measure them accurately. So if we combine those graphs that we created, the sensitivity graph and the distortion graph, you end up with something that looks like this. So here, again, this is as a function of power reaching the mixer and our signal-to-noise ratio, or signal-to-distortion ratio. You see that where the noise and the distortion curves intersect, these are the points at which we get the maximum dynamic range. And it can sometimes be different if you're trying to maximize second-order or third-order dynamic range. So as you can see here, we would have two different operating points on the mixer. There's one other thing that can limit our dynamic range, and again, that's phase noise. And so if I'm at some offset from the carrier signal, there will be some phase noise associated with that point. So again, depending on your application, you might be worried about close-in signals, maybe at a kilohertz offset, or maybe all the way out at a megahertz or more. So again, it's something else that may limit your ability to look at large and small signals simultaneously. Now, if you're comparing the performance, dynamic range performance of different analyzers, it's important that you do an apples-to-apples comparison because sometimes different people refer to dynamic range in slightly different ways. Some people might talk about, what's the maximum signal I can look at and what's the smallest signal I can look at. And that's what we would normally term as the measurement range. Or some other people might talk about the mixer gain compression point, the 1 dB gain compression to noise, or you might be trying to optimize for third order or second order distortion. So again, there's different ways to define that dynamic range, and you just want to make sure you're using comparable terms. All right, so to summarize, to get the best dynamic range, you want to, again, optimize sensitivity by using the narrowest resolution bandwidth and the least amount of attenuation possible and some amount of averaging. But at the same time, you have to make sure you have enough attenuation so that you're not experiencing distortion, and you want to kind of balance those two things. All right, so those are some of the kind of classic topics. I'd like to spend a few minutes now looking at some of the modern capabilities that have been introduced in recent years and how those can be very useful for looking at the kinds of signals people are concerned with today. So I'd say one of the biggest developments in the last decade has been the transformation of the architecture from being a fully analog architecture to one that has much more digital processing capability. So typically on the front end of the instrument, you'll still see things like the attenuator and preselector filter and LO and mixer. But very quickly, once you get to the IF, we now go through an A to D converter. And at that point, you've now entered the digital realm, and so all the processing in the IF is now done digitally. And so we can do our FFTs or swept type measurements. And then, again, at this point, everything is done digitally, and we've replaced a whole lot of analog circuitry in the IF. Now, the good news, as a result of doing that, our overall measurement uncertainty goes down tremendously. So things like with our high-performance PXA analyzer, you can see that things like the switching uncertainty have been improved dramatically in frequency response. And things like reference level accuracy have essentially gone away, whereas in the past we depended on analog circuits to set that reference level. Since it's done digitally now, we can calibrate that out, and these things like ref level accuracy or resolution band switching uncertainty or scale fidelity are either gone completely or almost gone. So the overall measurement accuracy, you can see a huge improvement, much better accuracy as a result of going digital. Some other things that you can do now with the digital processing power is you can create a number of one-button measurements. So if I want to do things like occupied bandwidth or Jason channel power, CCDF statistics, or harmonic distortion measurements, these now become very easy to essentially build into the instrument, and by pressing a single button you can make that kind of a measurement. The other thing is, of course, there's a lot of different wireless standards that exist for cellular communications or wireless LAN and so forth, Bluetooth. Because they're standards-based systems, we can set up the instrument to go to the right frequency range and bandwidth and appropriate settings, so you can start making measurements on that standard right away. So if I was doing, let's say, GSM measurement or wideband CDMA or wireless LAN, again, very quickly I can set up the instrument to make that measurement. Now, just like smartphones, there's a whole bunch of apps that are available on spectrum analyzers these days. So if you want to make specific measurements like a noise figure or an EMI type measurement or measure to a specific wireless standard, again, there are applications that are optimized for those particular measurements, and so there might be a lot of measurements here that are available, and so if I was doing an LTE measurement, there might be several of these measurements here that I would want to make for that particular standard. So those are all now available as applications. Some other nice display capabilities that are available now are things like spectrogram. So up here at the top we have our traditional spectrum display, but imagine if we flip this 90 degrees so it's poking out of the display, and so we would show here on the bottom display the x-axis here is frequency, the y-axis is time, and so we show how that signal varies with time, and we use color to indicate amplitude. And so here you can see that this particular signal was bursting on and off quite rapidly. Then there was a long gap where it was off, and then it came on again, stayed on continuously. So it's another way of looking at the signal, and it provides us more insight into what's going on, not only in terms of frequency and amplitude, but also in time. Okay, another example of some of the new capabilities, we have things like trace zoom that are available now. So let's say I'm looking at a wide spectrum here from 30 megahertz to a gigahertz, and I see that down here at the low end there seems to be some signal activity. These are kind of the largest signals on the screen, so I can place that blue band around it, and I can immediately zoom into that area and see that in much greater detail. While I'm still monitoring the wide spectrum, I can look here in much closer view and see that indeed there's several narrowband signals present there. Now, historically, RF and microwave signals were always on a 50 ohm cable, connectorized type cable, and we're finding that now more and more there's greater diversity in the way RF and microwave signals are available. In particularly on RF integrated circuits, very often instead what you get is differential I and Q outputs, and so rather than one single connector, you might need 4 connectors, 2 for I and 2 for Q. And so some analyzers have baseband IQ inputs available at the baseband to directly input those signals from a chip, let's say. And it may not necessarily be 50 ohms, it might be a high input impedance. But once you go through that part of the circuit, then eventually you get to the IF and you're going to treat the signal just like you would any other, digitize it, and then do your processing. Another trend we've seen a great deal is using wider and wider bandwidths. We see this, say, in aerospace and defense for things like radar systems and satellite signals and secure communications. In the commercial world, things like wireless LAN, WiMAX, and the new LTE standards are using wider and wider signals, and so it's important for the analyzer to keep up with those kinds of signals. And so here, for example, on the PXA, we have a number of different resolution bandwidth choices that are available. So the standard unit has 10 megahertz bandwidth maximum, optional to 25, and then more recently we added 40 megahertz and most recently 160 megahertz bandwidth options. So again, depending on the type of signal you're looking at, you may need much wider IF bandwidths. Now, on this, in particular on the 160 megahertz bandwidth, notice we have a very powerful FPGA and ASIC, and those are key to our next new capability, which is real-time spectrum analysis. And this is where we use that FPGA to do extremely fast FFTs, almost 300,000 FFTs per second. The advantage of that is that because we can process so quickly, the processing time is actually less than the acquisition time, which means that we can look at the signal 100% of the time. So that's extremely useful for fast transients and things that may not be present in time for very long. All right, finally, I'll just wrap things up by saying because there's so many different applications, Agilent offers a number of different models to meet different requirements. And so we have our X-series analyzers, starting with the CXA all the way up to our flagship model, the PXA. And they have different levels of RF performance in terms of sensitivity and dynamic range and frequency range and so forth. But they all use the same operating system and user interface. So if you know how to operate any one of those, you could sit down on one of the other models and it would behave exactly the same way. There's also many applications where people have to take spectrum analysis out into the field. Maybe you have to climb an antenna tower and make measurements in some location like that. So having a portable battery-operated instrument can become very important. So again, there's a number of different models. We have our HSA, the handheld spectrum analyzers here, and then recently we introduced the Field Fox family of handheld portable instruments. Now, in addition to looking at spectrum and so forth, very often we have to do a lot of analysis of the signal, and for that we have the 89600 vector signal analysis software, which has about 70 different types of demodulation algorithms built in. So if you're trying to look at any number of cellular or wireless LAN kind of standards or even custom modulation, you can very easily demodulate and do great analysis with that software. And then finally, I'll just say that if you're interested in getting more information, we have a lot of great information on the web, both application notes and a number of brochures, and you can find these at www.agilent.com/find/SA. All right, so with that, I think we have a few minutes left for questions, and I just want to mention that at the very end, we'll have a very short survey. If you could please take the time to fill that out, we'd really appreciate that. That helps us improve these webcasts so that we can continue to offer information that is useful and relevant for you. So with that, Allison, I guess we're going to switch to the questions now.
Yep, great. Thank you very much, Eric. So we've got a few minutes left for questions today. So I'm going to start off with the first one here, and this one I'm going to direct this to Keith. And the question is, can the input mixer also function as a multiplier, in this case, of the low band mixer?
So the answer to that one is the input mixer is a nonlinear device that does produce harmonics of the mixing products. However, we only use the fundamental mixing product in the low band path. When measuring frequencies above 3.6 gigahertz in X-series analyzers, we use multiples of the local oscillator to be able to measure up to the upper frequency range of the analyzer.
Okay, great. Thank you. And another one here for you, Keith. Is internal attenuation a passive or active circuit?
We have two types of attenuation in X-series. The mechanical attenuators are passive devices. The electronic attenuators are active. The primary attenuation in X-series is the mechanical attenuation, and that's because mechanical attenuators can cover a wide frequency range up to 26.5 gigahertz or 50 gigahertz. For the low band path, in X series, we also have an electronic attenuator, and the advantage of the electronic attenuator is that it can switch faster than a mechanical attenuator.
Okay, thank you. We also had a question about RTSA concepts and if they could be explained some more. So we did provide a brief explanation today, but I also want to point you guys to some upcoming webcasts that we have next week as well as next month, and Katie put the registration links for those in the chat window. So if you're interested in those, please go ahead and register there. Our next question, Keith, this is for you again. Lucky you. Where can I find your application note on Spectrum Analyzer Basics?
So the Spectrum Analysis Basics app note is application note 150, and that's what we kind of consider the Bible of spectrum analysis, or it's we refer to that to people all the time. And if you just go to Agilent.com and you search for application note 150, you will find it, and you will find other application notes in that series.
Okay, great, thank you. And Scott, I've got a question for you here. How does resolution bandwidth determine the sweep time?
Yes, as the answer to that is as that you reduce the resolution bandwidth, your sweep time slows down by the inverse of the resolution bandwidth squared. So therefore, you would want to set your resolution bandwidth so that it's small enough to achieve the sensitivity you need and also the selectivity you need. However, you don't want to use such a small resolution bandwidth that your sweep time is too long. Therefore, having an analyzer that has better sensitivity will allow you to sweep faster and not need to have such a narrow resolution bandwidth filter.
Okay, thank you. And one more question for you, Scott. How do I know what detector and averaging type to use when measuring a signal?
Okay, so when measuring CW signals, you would want to use the peak or the normal detector. However, when measuring noise or noise-like signals, then you would want to use the average or the sample detector. However, be careful when you're using the sample detector because you don't want to miss a CW signal, so just ensure that your resolution bandwidth is greater than the span divided by the number of trace points minus 1.
Okay, great. Keith, I've got one more question for you here. Can I use a signal analyzer as a network analyzer?
So a network analyzer is normally used to measure S11 and S12 type parameters. You can add a tracking generator or source control to a spectrum analyzer to enable scalar network analysis measurements. Our newer FieldFox handheld analyzers combine a spectrum analyzer and a network analyzer into one instrument.
Okay, great, thanks. And it looks like that's all the time we have for questions today. If you asked a question and we haven't been able to answer it yet, we will follow up with you on that by email. So before we close, Eric, do you have any closing comments for us today?
Sure. Just that, again, with the 1 hour we have available here, we had to do a very quick overview of this huge topic, and so there's a lot more detail that I'm sure a lot of you are interested in. So again, I would encourage you to take a look at our website, and we have a lot of great application notes that go into much more detail to talk about various topics that we've just touched upon here. So please take a look at that, and I think you'll find some good information. All right, thank you.
Great, thank you, Eric, and thank you, Keith, Scott, and Bob for helping answer questions today. And as we wrap up today's presentation, remember that we will email you a link when the on-demand version is ready to view, along with a copy of the slides. If you're viewing the on-demand version of this webcast and have a question about any of the material, please email Eric. His email is Eric, that's ERIK_Diez, D-I-E-Z, @agilent.com. And I'd also like to remind our on-demand viewers that we'd still like you to complete the webcast survey that will automatically launch at the end of the webcast here. And thank you to all of you again for attending today's event, Signal Analyzer Fundamentals and New Applications, brought to you by Agilent Technologies. please visit us at agilent.com/find/SAWebcasts or SGWebcasts for more details, and there you can register for our upcoming webcasts as well. The copyright of this presentation materials is owned by Agilent Technologies. I'm Allison Douglas, and thank you for joining.